Watch this flat, abstract painting instantly snap into a fully volumetric 3D object, expanding outward so we can smoothly orbit its back and sides. Reconstructing 3D space from a single 2D image is an under-constrained mathematical problem. Tracing the projection lines of a 2D circular shadow backward proves that a 3D sphere, a cylinder, and a cone can all cast that exact same silhouette. Traditional 3D neural networks struggle to solve this because they attempt to regress volumetric shapes directly from limited, small-scale 3D datasets. To bypass this data bottleneck, researchers abandoned the 3D-first approach. Instead, they turned to internet-scale, generative 2D models. The team set out to test if the latent spatial knowledge hidden inside massive 2D diffusion models could be repurposed to solve the problem of 3D reconstruction. That inquiry drives a research paper titled Zero-1-to-3, developed at Columbia University. The authors designed a mechanical shift in how we interact with diffusion. They transformed a standard text-to-image architecture into an image and pose-to-image model. In this system, the word pose has a strict definition. It refers exclusively to the relative camera viewpoint coordinates, the exact mathematical angle from which we observe the subject. Welcome to Gradient Daily. Today we are going to break down the exact neural architecture that makes this pipeline possible, working entirely from first principles. Bridging this specific architecture connects the limitless creative vocabulary of internet generative art with the strict deterministic spatial constraints required for robotics and augmented reality. To understand the architecture, we first need to look at the 2D geometric prior. Think of a forensic sketch artist. When they draw a profile view from a frontal photograph, they rely on a learned understanding of human facial anatomy to infer the missing depth. Models like Stable Diffusion possess a similar implicit prior. By analyzing billions of 2D internet images, they have learned precisely how shadows wrap around curves and how perspective shifts across different surfaces. The architectural challenge is access. We need a way to force this model to accept precise geometric controls instead of natural language text prompts. The solution begins by isolating the specific rotation, or R, and translation, or T, matrices. These mathematical coordinates flow in and concatenate with the RGB image embedding into a single data stream. This combined geometric and visual data then flows directly into the denoising units cross-attention layers. By overwriting the standard text encoder with hard camera coordinates, the researchers mutated a creative image generator into a deterministic 3D rendering engine. But this introduces a massive bottleneck. Where does a research team acquire millions of perfectly paired images, all labeled with exact R and T camera data, to train the model? They source it from synthetic 3D CAD datasets, specifically a massive repository called Objaverse. To integrate this data without destroying the base model, they use a fine-tuning philosophy similar to training a bilingual translator. The pre-trained diffusion model acts as the master poet. It already possesses the vast visual vocabulary of natural internet images. The synthetic CAD dataset acts as a strict grammar textbook. It contains no interesting textures, but it teaches the explicit mathematical rules of camera angles. During fine-tuning, the network observes a textureless 3D CAD model rotating at exact degree angles. It maps those angles to neural network weight updates, learning precise geometric control. To protect the master poet's vocabulary, the loss function includes a critical safeguard. This prevents catastrophic forgetting, ensuring the model retains its ability to generate natural images while absorbing the CAD rules. This hybrid training results in a model enforcing strict CAD geometric rules while maintaining the visual diversity of its original internet-scale pre-training. At this stage, the model is still only generating flat 2D pictures from novel angles. We need to transition from 2D pixel generation to carving an actual 3D mesh. The system builds this using a neural radiance field, or NeRF. This is the ultimate volumetric representation it wants to construct. The optimization loop between the 2D model and the 3D NeRF works like a blindfolded sculptor taking instructions from a group of photographers. The Zero-1-to-3 model acts as surrounding photographers, flashing sharp 2D constraints onto a central workspace. The central NeRF receives this error loss data, systematically carving away incorrect volume until the blurry blob sharpens into a distinct 3D object. This specific mathematical feedback loop is called score distillation sampling, or SDS. SDS allows the 2D diffusion model to act directly as a loss function for the 3D volume, evaluating and penalizing the NeRF's geometry. The 2D diffusion model never actually builds the 3D shape itself. Instead, it acts as an omniscient spatial critic, guiding a separate 3D sculptor until geometric perfection is reached. When tested on real-world inputs, the model revealed an extreme capability for out-of-distribution generalization. This means the model can successfully process and reconstruct input styles it never explicitly saw during its synthetic fine-tuning phase. We call this a zero-shot capability. We can prove this zero-shot performance by feeding the model a flat impressionist piece, like this Picasso painting. It successfully extracts 3D volume from a completely non-photorealistic visual domain. This succeeds because the synthetic CAD fine-tuning only altered the model's geometric controls. It left the base network's internet-scale understanding of art and texture completely intact. Prior state-of-the-art models like Point E fail instantly when fed non-photorealistic inputs because their architectures rely entirely on pure 3D datasets that lack diverse artistic styles. Paradoxically, possessing strong 2D prior knowledge makes a network vastly more robust for 3D understanding than exclusively training it on pure 3D data. But we have to establish exactly where this architecture breaks down mathematically. The system operates on a strict baseline assumption. It requires a single, centrally focused object and severely struggles if the input features heavy background occlusions. This leads directly into the most notorious generative failure state in this field, the Janus problem. Because the 2D prior lacks strict global 3D multi-view consistency, it optimizes each view independently. This causes the model to hallucinate a scrambled, mutated second face on the back of a character's head. While 2D diffusion is a brilliant geometric engine, the next frontier of machine learning research requires enforcing rigid, global spatial consistency across all generated views simultaneously. To summarize the poor mechanics, first, internet-scale 2D diffusion models hide astonishingly powerful implicit 3D priors. Second, synthetic datasets can successfully teach precise geometric control without overriding the model's natural image understanding. Third, Zero-1-to-3 demonstrates that leveraging internet-scale 2D pre-training enables 3D generation to generalize across visual domains where models trained purely on 3D data fail. If you found this architectural breakdown valuable, like the video, subscribe, and hit the notification bell for the next Gradient Daily Deep Dive.